So I hope you can still hear me. I'll just proceed. I've started the recording. So the topic we shall cover is this, Cosette's and Lagrange's theorem. So before we proceed, we set up, we define a relation on a group G as follows, that two elements in the group will be related if this product, the product of X and the inverse of Y, is an element of this subgroup H. So this is a relation we define on the set G. So you fix a subgroup of G and use it to define this relation. There are some special cases here where the subgroup is the whole group and the subgroup containing just the identity element, but this is not of importance now. So this now an example of such a relation. We pick the group of integers. And of course, when we say group of integers, the underlying assumption is that the binary operation is addition. And then we pick a subgroup of that group, which consists of all multiples of n. So H is a subgroup. And since the binary operation is written additively, instead of writing X multiplied by Y inverse, we have X minus Y here as your. So this is basically the set of all this translates to the following, that X will be related to Y if X is congruent to Y modulo N. In other words, if a difference between X and Y is divisible by N. So that's an example of this kind of relation, but with a concrete group, where the group in this case is the group of integers under addition, and the subgroup is the subset of the integers consisting of the multiples of N. So that shows the example. So there's something special about this relation. We shall look at that in a minute. So if you have, for any given subgroup, we make the following claim, that this relation defines an equivalence relation, which is consistent with right multiplication. So what it says is the following, what makes it consistent? This is what we mean by being consistent. But the first thing we want to prove is that it's an equivalence relation. For you to check that's an equivalence relation, you need to check all these properties. You need to check the reflexive property, which holds because any element multiplied by its inverse will be in H, because the identity is in H. The second one, if X is related to Y, it means XY inverse is in H. But then what does that mean? H is a subgroup, so the inverse of this, the inverse of all this, the whole of this product must be in H as well. So here we compute the inverse of that, and we end up with this. But this now means Y is related to X, because remember how we define the relation? We say X is related to Y. X, I'll use this as a shorthand for related. X is related to Y if XY inverse is in the subgroup H. So if you have it in reverse form like this, here. So this is now Y X inverse is in H. So this simply means Y is related to X. So this covers the symmetric property. We've covered the reflexive property for an equivalence relation. So this covers the symmetric property. What is left is a transitive property. So here you assume that X and Y are related and Y is also related to Z, in which case these two statements will be true. XY inverse will be in H and YZ inverse will be in H. So if these two hold at the same time, it will be transitive if we can show that X will be related to Z. In other words, if you can show that XZ inverse is an element of H, which we proceed to do. So XZ inverse can be written, you can squeeze in Y inverse and Y here, and that and these two, XY inverse and YZ inverse, have already been set up as elements in H, so their product must also be in H because H is a subgroup. So this takes us to the conclusion that XZ inverse must be an element of H. So this what do you call it? This relation is transitive. It is also symmetric and reflexive, and that makes it an equivalence relation. So the last bit is to show that it's consistent with right multiplication. In other words, if you multiply each element by an element from the group on the right, then the relationship is not lost. It's still maintained. And that's easy to prove. So if XY inverse is in H, you can check that this product will also be in H. So if you multiply these two, you can simplify as that. You end up with XY inverse. So it's still in H. It's consistent with the right multiplication. So anytime you have an equivalence relation, then it will partition the set on which the equivalence relation is defined into equivalence classes. And the equivalence classes are usually disjoint. So here we define the equivalence classes, or rather try to extract the equivalence classes. So an equivalence class of an element G will be denoted by this. So this equivalence class will consist, the reason we specify H is because the relation is dependent on H, but H does not serve any value other than to identify that H is the subgroup that was used to define the relation. And you can vary the subgroup, so it's important to where there's a possibility of confusion, it's best to clear that by specifying the subgroup that is used to define the relation. So the equivalence class of G will be the set of all elements in G which are related to G. So we describe that here, but now this can be made more concrete. The elements that are related to G will satisfy this property. So that will be all elements in G which satisfy XG inverse is in H. So you can make a substitution, Y is equal to XG inverse, then you rewrite this. After that substitution, you end up with this setup. So you end up with all products YG, where Y is in H, right? So if you run through all elements in H, you simply end up with HG, which is what we call the left coset. So HG, if you were to write this out, HG simply is made up, since G is fixed, it's made up of all the products. So every subgroup must have the identity. So maybe EG, and it has several elements. So maybe the first one will be A1 multiplied by G up to the last one. If it's a finite group, up to the last one. It may not be finite, but for now, let's, for simplicity, we work with finite group to illustrate. So this is what HG is. You simply multiply everything in H by G on the right. So this is the equivalence class of G. That is a set of all elements related to G will be the left coset of H determined by G. Is that making sense?
Okay, yeah.
The videos I shared have more detail on. They have more detail. Only problem is they work with left corsets, not right corsets. But anything you can do with the right corset, you can do with the left corset as well. Most books, I think, have the other set of notes. The book I used, I think, had was working with left corsets, so I stuck to that. So here is a definition for a given subgroup of G. If you run through all possible values of G, you will end up with a number of sets of this form. And all of them are called the right corsets. These are just the equivalence classes again of the equivalence relation we defined earlier. So this gives an example of the right corsets of this subgroup NZ of the group of integers under addition. So if you are to write out all these left corsets, now the difference, this is about an abelian group, so you can write it commutes. You observe that on this one we put the G on the right hand side. If it's an abelian group, it doesn't matter which side you put it in. Z is an abelian group, so left corsets and right corsets will be the same. So in this case, you can put your the element that is determining the left corset on the left. It won't matter because the group is abelian. It's a commutative group. But if the group is not abelian, then the right corsets may not always be equal to the left corsets. So for instance, if we pick, just to illustrate this example, if you pick n is equal to 3, you should be able to observe that your left corsets will be, the first one will just be 0 plus nz. So that will just consist of all multiples of n. And the other left corset that you will have will be all numbers that leave remainder 1 when divided by n. Then the last one will be numbers that leave remainder 2 when divided by. So this gives you the set of, if you try to go beyond this, you will be repeating, you'll repeat yourself. So this gives you the set of all corsets, right corsets of this. If we take n to be 2, it gives you the set of all left corsets of this subgroup consisting of multiples of 3, sorry. Since we have 3 of these, n is 3. So all multiples of 3. This is a left, all the possible left corsets you can get for this subgroup of Z. Now, it can be shown that this, if you recall your work on equivalence relations, it's possible to write the element on which you've defined the equivalence relation as a union of all the equivalence classes. So if you collect all the equivalence classes, in this case, the left corsets for the relation we defined, the right corset, sorry, of the relation we defined, if you get the union of all of them, you get back the whole of G. So as an example, here, these are the left corsets. If you get the union of all these, you will get back the whole of Z. Since G is Z and H, we picked it to be the multiples of 3. And these are, you can see this if you write it out like this. So this first coset, it's made up of multiples of 3 because remember n has been picked to 3. We'll fix it at 3, so it will be made up of multiples of 3. And this goes on ad infinitum. And the same happens on the left-hand side, -3, -6, and so on. So this gives you the first equivalence class, or the right coset, determined by 0. Then the next right coset will be all those numbers that differ from 1 by a multiple of 3. So you simply add 3 to get 4, get 7, and so on. On this other side, you get, I think it's -2, -5, and so on. Then the last one is this. This last right coset. So all the elements that leave a remainder of 2 when divided by 3. So they will differ from 2 by a multiple of 3. That gives us 5 here. Gives us 8, and this keeps going like that. Here we have -1, -4, and this keeps going. So if you get the union of all this, you should recover the whole of Z, because the equivalence class always breaks a set into, it partitions a set into equivalence classes. In this case, we establish that the equivalence classes are these left cosets. And once we obtain all of them, the union will give us back the original group. You can also just manually see that now there's no number missing. If you start counting from 0 here, this will be 0, 1, 2, 3, 4, 5, 6, 7, 8. So that gives you a pattern. This will continue like this, 9, 10, 11, and so on. So you will get back the whole of Z, and you also see the same pattern on the left-hand side. So that covers the first bit. The second bit says that any 2 left cosets are either distinct. If they're not distinct, their intersection, so if they are distinct, rather, the intersection must be empty. I think that is a direct consequence of the equivalence relations, but it's not stated here. So, but this second property says if you have the intersection of 2, if the intersection of 2 left cosets is not empty, then they must be equal. It's the same thing. I think what was happening in between here was a mess. So there's a bit in between here that I think I was paying attention to and didn't see this last part. So it's actually this one. If the intersection of 2 right cosets is not empty, then they must be equal. And if any 2 different right cosets also will have nothing in common, the intersection will be empty. If it is not empty, they have to be equal. So this can be proved. I will leave this as an exercise, this part 2. It's not too hard to find the solution to this. It's in many books. It's also easily available online if you look for it. So you can say one more thing about cosets, that any 2 left cosets, any 2 right cosets have the same number of elements. So with that in mind, if any two left corsets, this map is a bijection between two left corsets. This map defined here is a bijection. So if it's a finite left corset, then any two finite right corsets will have the same number of elements. That's what this map shows. Because if you have a bijection between two finite sets, then they have the same number of elements. If it's infinite, they would still be equal. But then you can't count. So here you can only get the cardinality if the set is finite. So, but that is based on this map that has been constructed here. The map shows that you have a bijection between any two right corsets, and therefore the cardinality must be the same. Any two finite sets that have a bijection between them must have the same number of elements or the same cardinality. So we shall use that at some point, that any two right corsets have the same number of elements. So if you collect the number of distinct the number of distinct right corsets, that number is called the index of the subgroup H in G. And this is how it is denoted. So for instance, if we go back here, this subgroup, the multiples of 3 is of index 3 because it has 3 distinct right corsets. So with the discussions we have had in mind, we can set Lagrange's theorem. Now, how it works is this. Let's try to use a diagram. So if this is a group G, let's assume it's finite. Then you have the equivalence classes. Remember, we are saying the equivalence classes are disjoint. So let's assume this one has, is it 5 or 6? There are 5. Let's assume this one has 5. So in each equivalence class, we are just looking at the left corsets. Suppose the subgroup we're working with is H. H will also be one of the left corsets because that is or the right corsets. I keep saying left because I'm used to saying left. So I will try to be consistent with right. So the subgroup itself will be one of the left or of the right corsets because you can obtain it as a corset if you use an element that is already in the subgroup. So if you use an element that's already in H will be definitely be one of, as long as A is an element in H, this will be true. So again, this is a result that you can try to prove. So H is one of them. Then you can list all the remaining right corsets. So here we stop. This is A3. We are assuming there are 5. There can be more than 5, but for simplicity, we have a total of 5 distinct left corsets. So again, we have said that each of them must have the same number of elements. So suppose the number of elements, say, in the subgroup is M. So in this case, since if you want to get the total number here, you simply multiply the number of elements in the subgroup by the number of distinct left corsets. So 5M here will give you the number of elements in the whole group. So 5 here is the index. index of the subgroup H because that's the number of distinct left cosets. M here is the number of elements in the subgroup. And the product gives you total number of elements in the group. So that's what Lagrange's theorem says. It says that if H and G are finite, then the number of elements in G will be given as a product of the index of H in G multiplied by the number of elements or the cardinality of H. So that's Lagrange's theorem. It follows from the discussion we had earlier that the equivalence relation will partition the group. Here what is interesting about the partition is that each partition will have the same number of elements. So just multiplying the number of partitions by the number of elements in any one of them will give you the number of elements in the whole group. And that is Lagrange's theorem. So we'll look at some consequences of this Lagrange's theorem. I believe you have, did we define the order of, I think we did. Or if not, it's in one of the topics that you are supposed to read. But if there's anything that doesn't make sense, you ask questions. So this one says if G is a finite group, then the order of every subgroup must divide G. So this is true because the order of every subgroup is the same as the number of elements in a right coset. And also you can see it clearly. If this is a subgroup, this number of elements in the subgroup is a factor of the order of G. The order of group is just the number of elements in the group. So the next one says if G is a finite group, then the order of A divides the order of G. So this is true because the order of A is equal to the number of elements in the cyclic subgroup generated by, did we use square brackets or these angle brackets? The cyclic subgroup generated by A, the number of elements in that cyclic subgroup. So if the number of elements in the cyclic subgroup generated by A is known from Lagrange's theorem, we know that it must divide the order of G. So the order of any element in G must be a factor of the order of G. So is a good exercise for you here, this Fermat's theorem. Again, this is easily found in many textbooks. Or if you look it up online, you should be able to find the proof. So again, I leave this as an exercise. The Fermat's theorem. It simply says that A raised to the number of elements in the group must be equal to the identity. So another good corollary here. It says if N and M are co-prime, if the GCD is 1, then M raised to phi N. Phi N is the Euler's no. What is this? Now, what is that? Is it Euler's function? The number of integers that are smaller than n but co-prime to n. say Euler's phi function. So for instance, if you are considering a number like 8, so this the value of this should be equal to the number of integers that are smaller than 8 and co-prime to 8. So let's see if we can list them. One of them is 1, the other one is 3, 2 and 4 are not co-prime to 8. We have 5, 6 is not co-prime to 8. We have 7. So the Euler phi function is of 8 will be equal to 4. If you have a prime number, the Euler phi function with the argument equal to a prime number will usually be equal to p minus 1 because all integers, all positive integers smaller than p, the prime number, will be co-prime to p. They will not have any common divisors with p because p is a prime number. So this is a special case. So for instance, the Euler phi function of 5 must be equal to 1. So this is the one we want to prove, but it's a special case of Fermat's-Little theorem, which says that the order of any element in the group raised to the number of elements in the group will be equal to the identity. So this requires you to consider the multiplicative group of integers modulo n. This is Zn star. So the multiplicative group of integers modulo n will simply be the elements that are in Zn but and co-prime to n. So that leaves out 0 since you work with the multiplicative group. So to distinguish it from Zn, usually you have the superscript here. The star tells you that you're working with the multiplicative group of integers modulo n. Now, since this multiplicative group is simply made up of all integers that are co-prime to n, the number of elements in Z star n, so the number of elements in Z star n, which is a group, will simply be the same as the Euler phi function of n. So if you apply Fermat's-Little theorem, the identity element in Z star is 1. If you pick any element in Z star, the number of elements in Z star will be. So this will always be true. Pick M. I've used A, but you can use this theorem uses M. So this for any M that satisfies this property, this will be true. But then it's because it sits inside a group, and groups have this. They obey this property, the Fermat's-Little theorem. So you can if you take n to be prime, then this now reduces. If n is p, a prime number, then the Euler phi function is just p minus 1. So it reduces to this. This is what it will reduce to. So again, you can now write this one as a special case of where n is prime. A special case of this theorem, but where n is prime. So that is a corollary now. So n is a prime, and we call it p. So, but this is obtained from from this top, from this one, if you look at properties of integers, modulo arithmetic allows you to do the following. If M is co-prime to P, and in this case it is, then it's possible to multiply both sides of the equation and still retain the congruence. So if I multiply this side by M, I end up with MP. And this side, if I multiply it by M, now I have M modulo P. So that is where this comes from. Yes.
There's someone waiting on the lobby.
Okay, I've admitted them. You need to mute the mics. That covers. So this you need to, if you haven't already done it, you need to sit down and read this carefully so that it sticks. So the other statement that is important says that if G is of prime order, then it must be a cyclic group. This follows from the fact that the order of if A is an element different from the identity in the group, then its order cannot be equal to 1. But now if its order cannot be equal to 1 and it divides G where G is a prime number, the only other option is that the order of A should be P, the prime number which is equal to the number of elements in G. Right? So that leaves you no option than to conclude that the cyclic subgroup generated by A must be equal to G. So the details of this is as follows. One thing that we know is that the cyclic subgroup generated by A cannot be bigger than G. But now this argument takes us one step further and tells us that the number of elements in the cyclic subgroup generated by A is the same as the number of elements in G. Why? Because the number of elements in G is prime and the order of A is prime. So the number of elements in the cyclic subgroup generated by A should be prime as well, because it cannot be equal to 1 unless A is equal to the identity element. So these two together, this is a subset of the group, but a subset has the same number of elements as the set, the mother set. So it means that the two must be equal. In other words, the cyclic subgroup generated by A must be equal to G. But then what this means is that G is a cyclic group because we've shown it is generated by this one element A. It is equal to a cyclic subgroup, which is a whole of generated by A. Any element that is not the identity will generate the whole group as long as the group is of prime order. So the next one also uses a similar argument to show that if you have two, this should be H1 and H2. I think that is a typo. If you have two subgroups, finite, and their orders are co-prime, then the intersection will only contain the identity element. So as long as you have two groups and their orders are co-prime, then the intersection will only contain the identity element. Again, the proof is here, uses the same ideas as the thing is that the intersection of H1 and H2 must be a subgroup. And the number of elements in any subgroup must divide the order of the group. In this case, it must divide both the order of H1 and the order of H2. but the only number that does that is 1 because the orders are co-prime. So the number of elements in the intersection can only be 1, and if that is the case, then the only element that can work is the identity. So this simply now defines the left cossets. So it's useful to know them. At some point, when working with normal subgroups, we will need to use both. But the difference is now you simply multiply on the left instead of on the right. That's the only difference. But all the other properties that hold for the right cossets will also hold for the left cossets. So if you want to generate the left cossets, the relation that you define on G would have to switch. Remember the one we defined earlier said that X is related to Y if XY inverse is in H. So if you change this relation and now put it as X is related to Y if X inverse Y is in H, then this one will give you the left cossets as the equivalence classes. This first one gives you the right cossets as the equivalence classes, and this one gives you the left cossets as the equivalence classes. I think the videos I shared work with this second case, the ones for the undergraduate class. So if you wish to look at the second case, you'll be able to find it in the videos. I don't know, did I share the videos only or I also shared the slides? The slides that go with the videos.
Videos only.
I only sent the YouTube links. I should share the slides, but Harrison should have the slides, I think. Ama walitupa kila kitu. But anyway, that can disappear if it was on a phone and you no longer have the phone. But I will share. I will share the slides for the undergraduate class if you want to have them. So this theorem also tells you that there's a bijection. Basically says the number of left cossets is the same as the number of right cossets, and so you can apply Lagrange's theorem using left cossets as well, if you wish. So let's look at the next theorem. So this theorem says, suppose you have 3 groups where K is a subgroup of H and H is a subgroup of G. So if the index of K in G, since K is a subgroup of G, you can talk of the index of K in G. And also since H is a subgroup of G, you can also talk of the index of H in G. And since K is also a subgroup in H, you can talk of the index of K, of H in K. So if the index, if these two are finite, this GH and HK are finite, then this one will also be finite because this is a relationship between them. So now K being smaller will definitely have a larger index. Usually, if you work, that makes sense. it will have a larger index than H in G. So H in G multiplied by the index of K in H, of H in K, will give you the index of K in G. So the proof again is given. It's given using left cosets, but it doesn't matter which one you choose to use. You could use the left cosets, you could use the right cosets. They have the same it will work either way. So I will leave this, try to prove it. So there are, I think there are additional theorems here. They all have proofs written in the notes. I think they are not too hard to follow. So you have to burn some midnight oil to do these ones. I suggest that you do these as exercises. As usual, if you have trouble, please make sure you ask in the when we meet in the class. Maybe we can try to do this exercise. This one that says we write Z15 star into left coset with respect to the subgroup, cyclic subgroup of Z15 generated by 7. So first of all, let's list the elements of Z15 star. I need to get a pen that can, I'm using the mouse to write, so I'm not very fast. But you can see what I'm writing.
Yes.
Yes.
So what are the elements of Z15? We have 1, the next one is this Z15 star. What are the elements? Remember we said these will be elements that are smaller than 15 but co-prime to 15. So the next one will be? And the next one will be what?
4.
Is, pardon?
4.
Yes, that's correct. 5 can't work because 5 divides 15. 6 also cannot work because 6 and 15 have 3 as a common divisor. The next one is 7.
7.
Then 8 as well. 9 and 10 can't work. So 11. 12 can't work.
13.
So 13.
10.
And 14. Is that complete? I hope we have everything. So this gives you Z15 star. So this forms a group under multiplication, modulo 15. Now we need to find the cyclic subgroup generated by 7. So to do that, we need to find all the powers of 7. So 7 is one of them. 7 squared will give us what?
9.
Hmm?
9.
It can't be 49. It has to be one of these numbers
4.
to give us 4. What about 7 cubed? You have to, we want to generate the cyclic subgroup. 7 cubed will be what? So you don't have to use 49. Now you can just use 4. Multiply 4 by 7, you get 21. That gives you 6. So you don't have to, because we did this, we multiplied 7 by itself and got 49. But now 49 is not what we wanted. We have to reduce this modulo 15. So our answer now becomes 49 is congruent to 4 mod 15. So we pick 4. So if you want to get 7 cubed, you could still do 49 times 7 to get 7 cubed, but that will only make you work with a bigger number, makes your work harder. So you can just use 4. Instead of using 49, you can still work with this as 4 times 7, because 4 is 7 squared, and multiplied by 7 is like 7 cubed. So 21 will be congruent to 6, and so on. So that's how I get 6. So you can keep doing this. 6 times 7 is no. 6 times 7 is 42, and 15 modulo 15. This will be what? Six should not be there. Something is not right. 6 is not co-prime to 15. So I've done. So 4 times 7 is 28. I was working it out as 21. So 28 will give us what? 13, right?
13.
Yes. So you have to help me out here. Let's keep going. The next one is what? 91 will give us 1. So I think this gives you the full. This gives you the full list, so you can write it out neatly. Now that we know the cyclic subgroup generated by 7, this will be 1. So that just write all the elements 1, 3, 4, and 7. It's a subgroup with 4 elements. So now we need to find the left cossets. So if you call this one H, left, yes, for left cossets. Yeah, let's compute the left cossets. So left cosset simply means you multiply on the right. So we can ignore anything that is already in the subgroup, will not give you a different left cosset. So it only makes sense to compute left cossets that are determined by elements outside the subgroup. So let's pick something that's outside the subgroup. So for instance, we can pick 2. So what is 2H? We are getting the left cosset, so that's why I'm multiplying on the left. So what this simply means is you multiply every element in here by 2, but you have to reduce that modulo 15. So 2 times 1 is 2. 2 times 3 is 6. 2 times 4 is 8. 2 times 7 is 14. So this gives you the second left cosset. Pardon?
Are we using 3 or 13?
Where are we using? Sorry. Oh, this is a mistake. This should be 13.
Yeah.
It's because of the way I'm writing. I also can't see my own handwriting clearly. So this is a 13. I wrote it as 3. Thank you. So you can rearrange. 13 is the biggest, so maybe you should put it at the end. So now What does that change anything? 2 times 13 will be 26. Let's just rewrite this again. So 2 times 1 is 2. 2 times 13 is 26. That will give us what, 11? Two times 4 will give us 8. And 2 times 7 will give us 14. I think now this should be correct. So this is the other left coset, but you will notice something. These two left cosets already, their union is the whole of Z15. So it means you can't get any new left cosets. You have exhausted them. You could try and say, try something like 13, not 13. 13 is already in H, so if you multiply it by H, you won't get anything outside H. You could try with any other element here, and you will see that you still end up with the same thing. So when you found all the left cosets, or rather you can know that you found all the left cosets if the union of the left cosets that you have will be equal to the whole group. So there are no new left cosets. The other way you can know if you have found all the left cosets is the index of the left coset in the group is simply the number of elements in the left coset in the group divided by the number of elements in the left coset. So in this case, the number of elements in the group is 8. Number of elements in the left coset is 4. If you divide that, you get 2. So you can't get more than 2 distinct left cosets. So this takes care of all the left cosets. And that's it. So any other left coset you try to compute will coincide with the one of these two. So this other one now uses some property. So let's put this as 7 raised to n. This will always be the same as 7 raised to r, where r is the remainder. When you divide by 15, the remainder when you divide r 15 by n, or rather n by 15, so if you want to get the 7 raised to 350, you need to get the remainder when 7 is divided by 350, which is what? When 350 is divided by not divided by 15, divided by the order. This is wrong. You have to divide it by the order of 7. So R is the remainder when n is divided by the order of 7. The order of 7 is 4. So 350 divided by 4, what is the remainder? Is it 2? The remainder is 2. So 7 raised to 350. 350, not 30, is the same as 7 raised to 2. The remainder when 350 is divided by the order of 7. 7 has order 4 because it generated only the cyclic subgroup generated by 7 has 4 elements, so the order of 7 must be the same. That's 4. So 7 raised to 350 is 7, same as 7 squared. What is the order of 2? You can check the order of 2 by you just keep raising the value of 2, getting 2 subsequent powers of 2 until you reach the identity to get the order. So the smallest power that gives the identity is the order. So 2 squared is 4. So the order will definitely be 4. Because it can't be 3. 3 does not divide 8, so the order cannot be 3. So 2 squared is 4. 2 cubed is 8. And 2 raised to 4 is 1. So the smallest integer that gives the identity is 2 raised to 4. So again, 2 is of order 4. So 2 raised to 1,000 will be the same as 2 raised to some remainder when 1,000 is divided by 4. So when 1,000 is divided by 4, what is the remainder? You can hear me?
Yes.
So what's the remainder when 1,000 is divided by 4?
None.
So it's the same as
Yes.
1. So in general, if you have 2 raised to 4, a multiple of 4, this will always be equal to the identity, where 4 is the order of the element 2. So I think we can stop there, but next week we can try to find more time to cover more topics. Today we delayed a bit with the connection problem that I had, but I think that's enough for one class.
Yes.
The other thing is, since you are advanced students, I'm expecting you to be reading ahead in your own time. So when we come to class, we should not be, you should not be seeing this for the first time in class when we're having the class. So normal subgroups is an interesting topic. We'll cover it. Are there any questions? Someone had been kicked out of class again.
No.
I'm seeing the.
No question.
Yeah. If anyone is kicked out, maybe you should be alerting me. Sometimes when I'm looking at a slide, I don't see what is happening on the.
Okay.
On the screen. So I will stop the recording and I will share the recording. I know I didn't share the previous one, but I will definitely share both of them.